So let's finish up by looking at two really quick algorithms, and maybe even quicker than what we just had, that we just looked at with the peak algorithm. And the first one we're going to look at is isEmpty. And isEmpty is simply going to check either the front reference or the back reference. So I'm going to choose front because I feel like it for no other reason other than that. You could use either one, they'd be equivalent. So we're going to need to have the front reference and scope for our algorithm here. Now we're checking to see if we've got this picture right here, right? If our queue is empty. That's why we could choose front or back, but I'm going to choose front just because I feel like it. So what are we going to do? All we're going to do is check if that exists. If f is equal to null, or if it contains null. If it is, or if it does, then we're going to return true. If it doesn't, then we're going to return false. It's that simple, right? And this is going to be a very, very efficient algorithm as well, right? It's only going to be two operations for this. Remember, we've got one of two scenarios. Either the queue is empty or it's not. So let's check scenario one. Is front reference equal to null? Does it refer to null? It does. As we can see right here in this scenario, in our empty queue, that is referring to null. So it's going to return true. That's what it should return because we're asking if it's empty. So it works in that scenario. Now what about the second scenario? Look at our algorithm. Does the front reference refer to null? That's false. So we skip down to the else and we return false. And that's exactly what we want to, because it's not an empty queue in that situation. So our algorithm here, isEmpty algorithm, works just fine. Now let's do some analysis. What's our big O? This test right here is always going to execute no matter how many nodes there are on the list. So that's one operation. Now either this return statement is going to execute or this return statement is going to execute. It's either or. You're only going to have one or the other based off of the result of this test right here, right? So it's plus one or the other. So this is going to be a big O of 2 algorithm as well, which we can rewrite as big O of 1 since it's a constant time algorithm. Easy peasy lemon squeezy. Okay, so now let's look at our clear algorithm. And our clear algorithm is going to need to have access to both the front and the back reference. Because what we're doing is we're emptying the queue. We want to reset it to an empty queue. So we want to have our memory set up like this, right? We want both the front and back references set to null. Now, it could be the case that we had a non-empty queue, or it could be the case that we already had an empty queue. Either way, it doesn't matter. We're going to go ahead and just set front reference to null and the back reference to null, because we need to put our memory in this state in order for it to be an empty queue. So does this work? Now, let's say that we call clear on an empty queue. Well, we're overriding the contents of the front reference with null, and we're overriding the contents of the back reference with null. So we end up basically where we started, but it does work. Now, what about for a non-empty queue, right? So it doesn't matter how long this queue is, it's not going to have any impact on our algorithm at all, because when we call this clear algorithm, we're going to change the front reference to refer to null, and we're going to change the back reference to refer to null. And when we do that, there's no longer any reference pointing to the front node. And so the garbage collector is going to come along and remove that from memory, and it's going to start this cascading effect, right? Any nodes following that previous front node are going to get deleted, and it's going to keep on repeating and so on until you get to the last node where there's nobody referring or no references referring to that last node. So it's going to be removed from memory as well. And so we end up with an empty list, which is exactly what we want. So that checks out and that checks out. Now let's do some analysis. This is super easy. We've got two operations that happen no matter what. So that's going to be big O of 2, which is constant time, which we can rewrite as big O of 1. So that's everything that I have for you regarding queues. So what did we talk about? We talked about what a queue is. We looked at some of the use cases for a queue. We discussed algorithms for an interface for implementing a queue data structure, as well as analysis on the efficiency of those different algorithms. As usual, if you're a student of mine and have questions about any of the content in this video or any of the other videos in our courses, feel free to contact me via Canvas email or stop by my Zoom office hours. Thanks for watching, and we'll see you next time.